Okay, so the image annotation task is usually done using KNN method. So it follows on the principle that similar images share similar labels. So basically we have to find for a given test image which images are similar to it, and then according to some greedy strategy or some algorithm, select labels from those images and assign to that test image. So this is a general setting which is used, but this has some problems. The feature vector of an image has so suppose it has d dimensions, but it is not necessary that all those dimensions contribute equally or contribute to a similarity measure. So suppose it may be case that one particular dimension is not giving much information in similarity measure, or suppose one subset of dimension is not giving any information. So in that case, that KNN method will not perform as good. So what we do is we try to so this is basically a feature selection problem. So this is posed as a metric learning problem. So what that means is each dimension is assigned some weight. So weight means how much a particular dimension contributes to distance calculation. So now this is an optimization problem. We have to find optimal set of weights such that the performance of any method is best. So this is called metric learning. So that is some improvement or variant of KNN method. So in all these three methods which are considered in this assignment, JEC, 2P KNN and TACPROP, they are variants of this basic principle, metric learning. So first is JEC. So JEC is a very naive method. So to solve this problem. So in this method basically we treat we assign each dimension equal weight. So that hence the name joint equal contribution. So I mean obviously this does not perform as good as the other two methods, cause it is equivalent to KNN. I mean, so basically we are averaging the distance and then learning the model or something. So this does not perform as good. So now we have TACPROP. So in TACPROP is better implementation of metric learning problem. So in this each dimension is assigned some weight. So and that weight is called relevance probability. So each dimension is assigned a relevance probability. So now the problem is to find such set of weights so that the relevance probability is maximum. So again this can be posed as optimization problem. So in this experiment we have considered 4 variants of TACPROP. TACPROP single distance, SD TACPROP where only a single distance is considered, and TACPROP ML, so that is metric learning. So in that, in SD variant only single distance is considered, and so basically that is not actually related to metric learning. So we want to find out how weights decay with distance. So that is, and in ML, so ML is metric learning of course. So now we have to find the relevance probability of each dimension. And there are the 2 variants of these 2 methods, sigma ML and sigma SD, where sigmoid transform to that sigmoid transform is used or sigmoid function is used. So the main reason behind using sigmoid is so in image annotation problem, each label can have different frequencies. So some labels will be highly frequent and some will be less frequent. So it is obvious that labels which are highly frequent will occur are have more chance of occurring in an image. So they'll automatically get high probability, and the rare labels will get low probability generally. So to avoid that problem, the sigmoid variant is used. So this boosts the probability of rare labels and suppresses the probability of frequent labels. So this tag prop. And for 2pKNN, so 2pKNN basically solves or this deals mainly with class imbalance problem. So it is possible. So in KNN we find nearest images of one test image. So it is possible that those nearest images don't have all the labels assigned to them. So it is possible that some labels are missed for the test images which should have been there. So to solve this problem, 2pKNN method is used. So it works in two stages. So in stage 1, semantic neighborhood of an image is considered, where those test images are found out which have at least one occurrence of each label. So in this case, the set of test images or some neighborhood of test images collected which has all the labels in it. So the class imbalance problem is solved using this. So now I'll quickly start with my findings. So these are the baseline performances under standard setting. So as we can see, they all conform to what the papers report. So they are consistent with the actual readings. So JEC performs is in 23% precision. So which is consistent with original. So and for others also we can see. So yeah, now comes the role of validation. So each method, all three methods have some hyperparameters, so which are empirically determined. So when we run the experiment, so what I did was I tried out some values, and then whichever value gave the best performance, I reported that or considered that. So instead of doing it manually, so this the concept of validation can be used. So in validation, we split data into training set and validation set. So and then on a training set, we train the model, and on validation, we check its performance. So whichever parameter gives best performance on validation, we use that parameter. So in JEC, so I consider two methods, JEC and 2pKNN. So in JEC, the only parameter is K. So I tried different values of K and checked the F1 score. So and yes, for feature 2 I use this. So this is the curve. So we can see for 4 to 5 and 4, 5, 6 all. So for 2 and 3 this is not performing as good. So we can see for 4, 5 and 6 this is giving a good F1 score. So K is equal to 5 is selected, which is consistent with the parameter used in the paper. And yes, I tried out on different training and validation splitting. So in this particular graph, I used the training size of 3000, and for validation I used 1500. So again, this is I ran the experiment again for different splitting. So in this setting, the training size is 3500, and the test size, or sorry, the validation size is 1000. So the results are almost same. So the choice of k is equal to 5 is optimal. So yeah, in 2pkNN there is one parameter, bandwidth parameter. So in this experiment that was empirically found. So and that was between 10 to 20 for each experiment. So I tried the same validation technique for this and found. So I varied the bandwidth parameter from 5 to 30, and as we can see for 15 this is giving optimal performance. So, and the measure used was F1 score. So yeah, this is again the same experiment with different train and validation split. So train split was, the training size was 3000 and validation was 1500. And yeah, this X label, so I considered from the bandwidth parameter of 5 to 30 with a gap of 4. So yeah, that is somewhere near, that is 15. So yeah, so that is consistent. So between 15 to 20 this is giving optimal performance. So this is the role of validation. So through validation we can find these hyperparameters. So now this is the third experiment, which is we have to find the performance per label. So that means the precision of any method per label. So this is the graph for frequency. So as we can see, this graph is skewed. So some labels have very high frequency, as some have very low or zero frequency. So this does affect the performance, which we'll see in later experiments. So these are the graphs for precision for using feature 1 and feature 2. So we can see that for some labels the precision is 0. So that is due to this skewness of the frequency of the labels. So some labels are not present at all. So that gives the 0 precision. So these are the plots for precision for under various experiments. So yeah, so in this section qualitative analysis is done. So we have to compare performance of one method against two. So when I ran the experiment, I found these set of images for which JEC performs better than TACPROP and 2pkNN. So these are the set of images, and for this experiment and for these set of images, TACPROP performs better than JEC and 2pkNN. So yeah, and for this section, for these set of images, 2pkNN performs better than JEC and TACPROP sigma SD. So now in this section we'll explore the class imbalance and class imbalance problems. So as we can see from the frequency distribution, so some labels have very high frequency and some labels have very less frequency. So this is class imbalance problem. So we'll induce the or we'll simulate the class imbalance problem by considering only a part of vocabulary. So although the frequency distribution is skewed, but all labels have some frequency. That means they appear in some images. So we only consider a part of or some very small part of the vocabulary, so that the class imbalance problem is induced. So for this my experiment, I have considered 25% of vocabulary size. So we can see that the performance in case after inducing class imbalance the performance of each method degrades. So yeah, so so we can see, these four bars are corresponding to 25% of vocabularies from starting. So first bar corresponds to first 25% and so on. So we can see the last 25% has the maximum performance. So that is obvious. So from So we can see from the frequency distribution that the last 25% labels have very high frequency. So it is more likely that they'll appear in an image. So we can see that the last 25% labels, or the last fourth bin, gives the best performance. So which is quite obvious. But the problem is for least or the low frequency labels, this method JC does not perform well. So we can see tag prop. So similar is the case with tag prop. So for the last bin, it is giving maximum performance, and for the first bins which have low frequency, it is not giving that good performance. So yeah, in this case we can see that tag prop gives the best performance in this setting. So where we remove these labels, or where we consider only particular bin size. So that might be due to its sigmoid. So as we can see, the tag prop sigma gives the best performance. That might be due to that sigmoid property, where it boosts the rare labels frequency and suppresses the high label frequency. So we can see this performs best among these. So now in this experiment, we'll randomly remove some labels from the data set, or from training data, and then we'll examine the performance of all the methods. So this is the graph which shows the frequency of labels before removing and after removing. So yeah, so we can see that in this setting 2p Canon performs the best. So 2p Canon using feature 2, yeah, so variant of 2p Canon performs best in this case. So this might be the cause of this, might be the reason, the main motive or the main advantage of 2p Canon is this only. So this shows that. So for a given test image, given test image, the neighbors of the image might not have all the labels in it. So as we can see, the other methods like JEC performs very bad in this case. So but 2p Canon, due to its semantic neighbor, due to its first phase where it finds a semantic neighbor which have at least one label, which has at least one occurrence of label, and then performs the metric learning task. So due to that property, this is performing best. So we can see, so relative to other methods, this is quite better. So yeah, so from this table we can see, so this performs the best in this setting. So the precision is 45, which is very good considering we have removed 50% labels. So yeah, so in this setting we are only considering the frequent labels, the most frequent labels in this. So in my experiment, I have considered top 25% labels. That means the labels which have top 25% frequency. So the performance is very considerably improved for all the methods, we can see. So that is intuitive. a label, so the labels which are more frequent, that are more likely to occur in an image, so that is why they are frequent. So it is intuitive that the performance of all methods will be increased. So these are the performance. We can see they are considerably improved. So yeah. But in this setting also, we can see 2pKNN and TAC-prop. So they perform equally. So in this setting, almost all methods perform equally good. Which is as this can be treated as an ideal case where all labels are which have sufficient frequency. So this is an ideal case. So now in this setting we'll consider only, only least 50% labels. So that means the labels which have least 50% frequency. So only those are considered. So it is obvious that the performance will be degraded because as the frequency of labels is very low, then it is likely that these methods won't find the true label of a given test image. So we can see that JEC, all performance have significantly dropped. But for TAC-prop, we can see the performance is relatively better. So it has around 20% precision, TAC-prop SD. And TAC-prop ML has this best performance. So in this, again this can be attributed to the way TAC-prop was designed. So in this case it will learn the frequency of the low frequency labels are boosted and the high frequency labels are suppressed. So this gives the better performance. So now coming to extension. So in this extension, my part was to design or propose alternate method to this KNN or the metric learning part. So I chose using ANN, but due to computation issues and time issues, I could not perform the experiment. But I designed or thought of how I solve this problem using ANN. So the data set which was given, we had training images and test images. So for each training image, we had the feature vector and its corresponding labels. So we can design a neural network where it will have three layers. So input layer, hidden layer, and output layer. So number of nodes or neurons in the input layer will be equal to the dimension of the feature vector of each image. So that will be number of input layers. So for hidden layer, hidden layer can be empirically found. So we can check, we can iterate for hidden layer size from D minus or D by 2 to D, or we can vary that and check which hidden layer size gives the best performance. And of course the output layer size will be equal to the number of labels. So 200 in this case. So now for each image we can feed the feature vector into the neural network, and then using backpropagation algorithm, it will learn the corresponding Y vector. So Y in this case is a vector of the labels. So for given X feature vector, it has to learn the mapping to Y feature vector. So using backpropagation we can do that. So for each training, so for 4500 images we can train this method, and when the algorithm converges, we'll have a neural network which will be trained, which will learn the mapping. So for when we input the test image, from that mapping it will generate the Y vector. So from that we can solve. So this is the extension. So with this I conclude my video. Thank you.